All right. Good day, good evening, good morning, wherever this video finds you. We are going to work with or talk about these topics today, which is to manipulate a vector's direction, a vector's speed, velocity, acceleration, and location vectors. Well, actually, that might be something we get into more next week. So the main thing that we're going to be getting into for this one is to apply vector motion to an object on the screen, which would be an object drawn in canvas, and then also to discuss magnitude and normalization of a vector, which is probably pretty much the most important thing, which is understanding what magnitude and normalization is when it comes to a vector. So of all these points, this is kind of the main focus of this video. These might be edited later on. So let's go ahead and get into the PowerPoint, and then we'll start having some fun. We've already gotten kind of an idea of what vectors are that I gave to you from our previous module. So again, this is kind of a deeper look into vectors, specifically magnitude and direction. So when we take a vector and we want to decide on how fast that vector travels, so any kind of direction vector that we have, such as 2, 3 going in this direction, negative 3, 1 is going in this direction, and 3, negative 2 is going in this direction. You could actually have multiples. You could take 3, multiply it by 2, and negative 2 and multiply it by 2. And you would have a vector that's going in the same direction, but just faster per pixel. So the vector itself is how much your object moves per frame. So when you think, if you're moving 3 pixels per frame, and let's say, well, actually, let's take, for example, this 2, 3. And let me go ahead and maximize this a little bit. This 2, 3 vector. Every frame, it is moving by 2 pixels and 3 pixels up. So that means it goes quite a distance in a frame. So if that thing's moving 2 pixels over and 3 pixels up every frame, just think about how fast that object is going at 60 frames a second. So you have a few issues that you got to deal with when you're dealing with vectors. One of them is you don't want vectors to increase outside of a certain range. About 20 is as fast as you want them to go. You don't want a vector with a magnitude more than 20. And so when I say magnitude, I'm talking about how far a pixel travels. So if we have a vector with 8, 12 for its velocity, that means that it's going to move by 8 and 12 pixels on the x and y axis every frame. That is just ridiculously fast, and it's not really practical. So what we have to do is often we get these vectors that for a direction that have a really huge magnitude, meaning that the direction of the vector can be expressed in numbers less than 8 and 12, and having it go in the same direction, and therefore have a less magnitude. And so you want to kind of differentiate between the vector direction and its magnitude. So when we one thing that we're going to be doing is called vector addition, but I want to kind of go into more on. We'll come back to this in a second. I'm not going to cover subtraction, multiplication, because the one that you really use is addition. And we're going to come back to this in a little bit. I want to get into more on the magnitude and direction. So let's go look at here, magnitude and normalization. So you can find the magnitude of a vector, and it's just basically Pythagorean's theorem. So you can think about the vector, and the 3, 4, and the magnitude is the slope or how far it's moving, the actual movement of your item. So we're saying here that y, it goes down 3 and it goes across 4. So this right here, the hypotenuse, is your magnitude. And that means that if you are going 3 down and 4 across, then that means your magnitude, how much you're actually traveling, is 14.4. So that's the measurement of this space and this space, and that just really is finding the hypotenuse on the Pythagorean theorem. So that the magnitude is how fast your vector is. So when we have a vector of 8, 12, 14 is a pretty big magnitude. You can kind of it moves 14 pixels every millisecond. That's quite fast. So just remember, when I'm talking about magnitude, I'm talking about the speed of the vector, and that literally is the hypotenuse of the vector, where it actually is traveling. And so when you normalize a vector, what you're doing is you are going to take its value and you're going to try to reduce its ratio so that you have the same direction, but it's expressed with a number between 0 and 1. So for example, the vector 8, 12, we can take and normalize it, and we find that the value 8 divided by 12, its ratio is 0.65. Now if we take this vector and we reduce it down to its smallest components, taking 8 divided by the same number and taking 12 divided by the same number, which happens to be the magnitude, we can reduce this vector and reduce its speed. And the best way to do that, to refer to a vector, is with direction, because once you know the direction of a vector, you can make it as fast or slow as you want. So the slowest that this vector can be expressed, or just its direction itself, is if you take the value of each coordinate and you divide it by a number, in this case the magnitude, and you get a ratio that's lower that expresses this the direction. So 8 divided by 12 is 0.65. That's the direction. 8 pixels by 8 pixels to the right, 12 pixels down. And if you take this 8 divided by 14, 12 divided by 14, you can express this direction with a number that's smaller. So that 8 can be now expressed as 0.554. That 12 is now expressed as 0.832. And if you take 0.54 and 0.832, you divide them and you get 0.65. So basically it's the same direction, except for instead of moving 8 pixels over, it's moving 0.5 pixels over per frame. And instead of moving 12 pixels per frame, it's moving 8.83 pixels per frame. So it's going in the same direction, but it's going slower with a smaller magnitude. So often you're going to need to find yourself expressing a vector in its smallest component, which is just its direction. And you can do that by normalizing the vector. Okay, so let's go back to adding vectors. So basically it's natural for adding a vector. This is where you're going to actually vector addition. All the other ones don't even, subtraction, multiplication, division aren't really big. Multiplication is just another kind of addition. But the vector addition is where it's at. This is actually how you apply force to a vector. So you can kind of think of this as, hey, let's say that two objects are going to collide. So when I refer to this direction, and let's say that the first object is going this direction, and then the next object is going in this direction. Let's say they smash together, going their same velocities. Well, the resulting velocity of this vector, this force or force vector, being applied to this vector is just adding them together. So what you can think about is, let's say that a ball is traveling, or a person is traveling in this direction here, and they get hit by a car going in this direction. Horrible example, but if a car is coming at a person that's going in this direction and it hits them in this vector, then the resulting vector is going to be those vectors added together. So let's actually go up here and get to the actual thing that I'm trying to talk about. Okay, here we go. Here it is. So when this vector comes in and collides with this other vector, that is adding the force of this vector to this vector here, and then the resultant force, or the resultant velocity of this vector, when this guy or this vector's force is applied to it, is just an addition. So now this vector's motion is going to be moving in this direction, and you can kind of think about something moving in this direction hits something moving in that direction. Well, it's going to kind of be in between. That's where it kind of goes together. So vector addition is where you actually are applying two vectors, and you can kind of think about it as one vector is colliding into another vector, much like if you were to throw two balls in there and hit one ball against the other. Well, pool tables are an excellent example. A pool ball that's traveling in a specific vector, when it hits, the resultant vector is going to be an addition of the two vectors traveling together. And that's kind of the physics of it. So vector addition is what you're going to be doing mostly when you're applying force vectors, which we're going to be covering in the next video or the next module. So very simple adding vectors. So vector addition is what you're going to be doing mostly when you're applying force to vectors. And that's something that's going to become more apparent. So these other ones, subtraction, multiplication, division, you don't need to spend too much more on it. Magnitude and normalization, that's important. Understand that. Spend time on normalization, study normalization and magnitudes using my examples and then from your reading. So out of pretty much this whole chapter, those are pretty much the big catches. Make sure you know what vector addition does, how that behaves, because that's going to be used when we add force to specific vectors, and then make sure you understand what vector magnitude and normalization is. Spend some time on those, especially in your reading, because now it's time to go have some fun. Let's play around with our template that we have available to us that we can use for our assignment. So I'm going to go ahead and give you a demo of our of assignment 1, and then you're going to extend it to complete assignment 2. So what we need to do is we need to take the supplied template and vector class and implement our own bouncing ball example. So let's go ahead and grab the template and let's see what we can do. To get this one done. Okay, so this is the template we're going to use for our homework. HTML template chapter 1. Let's go ahead and start up NetBeans. Okay, let's go ahead and open that project up. Template chapter 1. That's for chapter 1 of your second book. That's the nature of code. Not the other one. Okay, so let's see what we have here. It looks like we have an index that contains a math vector and a my canvas. Okay, and it looks like what we have is, let's just play this and see what happens. Okay, it looks like we have just a simple moving bouncing ball here. Oh, it doesn't look like we have a bouncing ball. Let's see what we have to do for our assignment. Implement your own bouncing ball example. Submit relevant code and screenshot. Can't we just use mover.js? I believe we can, because I think this example was actually done with hard code. Let's see, there is no mover.js in here. Okay. Let's go ahead and continue. I'm going to go ahead and pause real quick. All right, so it looks like my instructions say that we are supposed to be using mover.js and this template to complete this task. So we're going to go ahead. I've got the chapter 1 template loaded in. I have not downloaded mover.js yet. So we're going to go ahead and grab that. And I'm going to go ahead and show that in folder. And what's nice, really cool about NetBeans is once you download something, you can kind of just drag it over and add it to the project too. It's really cool. So now mover.js is in here, which means that we need to add mover.js to the canvas or to our index.html. And we'll just go ahead and go to the index.html. I already imported mover.js into the project. What I'm going to do is, since that's a library that is probably going to be taking advantage of the vector library that we started talking about in our last module, I'm going to go ahead and include it after the math vector, but before the canvas or your game, the game code. Okay. So this is going to be mover.js. Okay, so let's look at mover.js, and then we're going to do a little hack and slash and implement this mover object into our code. So let's do our save all. I believe we're good here. So let's go ahead and go to my canvas. Okay, so there's a few things that I just want to get rid of because I don't want to, because it's just too messy. A few things like we're gonna actually get rid of everything in here. Let's say here that we're just going to get rid of let's get rid of all this. Yeah, let's just get rid of it. Because we're going to use mover. Why do we have to hard code all this stuff in here? Let's just use an object like we should. Okay, canvas width and height. Let's get rid of that too. Okay, we can get rid of this. Okay, so then we just have our clear canvas. That actually can go into our update. Okay, and so let's get rid of this one. Okay. Now, clear canvas is no longer going to be used. I'm in the game loop now. Only the update and draw is going to be done, and we're going to no longer keep track of timing. So we just do an update and draw, pretty much. Okay, pretty simple game loop. Okay, so let's pretty simple game .js code. Let's go to mover.js and let's look at what it actually is. Okay, so it looks like this is pretty close to what your sprite is, except for this is going to be for something that could be a sprite, but is more for maybe like an enemy. It's a sprite that's not controlled. It's just a mover on the screen of some kind. So we're going to actually implement three variables or three vectors. That's going to be the location, velocity, and acceleration vector. Now, mass is something that we're going to be taking into consideration when we start doing our force, applying force to our vectors, and that's for the next module. Image, width, height. We're not going to do much for image for this one. We're not going to need it, but I put it in there just in case you wanted to add an image to the mover. We're going to just do a simple ellipse for this. But one thing that we need to do is that when you're dealing with vectors and movement on the screen, it always comes in with those three vectors. And there's kind of a little secret to it. Essentially, what we need is to do three steps. You adjust the velocity when you update your vector, you update your mover or your sprite, you adjust the velocity based on the acceleration. So think about this as your car. Your car is going a constant speed unless you decelerate or accelerate. So every frame you are going to have the chance to step on the gas. So this right here is basically adding the acceleration vector to the velocity vector, and making it increased based on what kind of acceleration you're doing, whether it's in the X or Y direction. So you step on the gas, your car's velocity increases. So you add that step on the gas acceleration, and the add function is really simple. All it does is take the x of the velocity x, add it to the acceleration x. Takes the velocity y and adds it to the acceleration y. So the amount that you step on the grass is directly added to the x and y values of the velocity. And you can step on the gas in the x direction or the y direction. Or you can decelerate with a negative value. Okay, so velocity then is changed. And then your location is adjusted based on your velocity. But here's the kicker. Every frame you must set your acceleration back to 0. You can't have constant acceleration. Basically that would be like if we didn't set this at 0, basically we would be increasing speed without time. That's kind of the way it is. So the secret of making this all work is that acceleration has to be reset to 0 every frame. Okay, then we call on our bounce edges function that we learned about last week. Now this one's new. This is where I constrain the velocity of the x and y values, the velocity of our mover, to just 20 pixels. So a magnitude, the x or the y value cannot have a magnitude greater than 20. If it does go above 20, I set it back to 20. Now this is what we call a ternary or a tertiary if statement, and the reason why I did it is because those are the fastest if statements that you can do, and there would be probably some better mechanics to implement this other than the tertiary if statement or ternary, whatever, however they say it. But this basically just turns the vector and makes sure it doesn't increase in speed above 20 pixels a frame. If it's moving 20 pixels a frame, that's going pretty fast. Your eye probably can't even see it. Then we're going to get into a draw, and for this one, all we're going to do is draw a circle, and that's going to be based on the location and the radius of our mover. So the radius of our mover, we're going to actually pass in. That's going to be an argument that we pass in. So we're going to instantiate some movers. Okay, so it looks like the draw is already doing it for our mover.js. And it looks like we have some apply force functions. That's fine. We got check edges. Okay, so check edges is where we can go around the world. Bounce edges is the one we did last week. So in our update function for our mover, we adjust the velocity based on the acceleration, adjust the location based on the velocity, and set the acceleration back to 0. Check for the edges. Do we need to bounce off the edges? If we do, reverse the velocity so it bounces, and make sure the speed does not get too high. So that's pretty much all we need. The apply force we're not going to be really doing, but all this other stuff is pretty much reset you're not going to do. So it's just going to be this bounce edges, and then draw the arc. If the image is null, we're just going to draw the arc, else we're going to draw the image that we send it. So for this one, we're just going to send it a null image, or a null for that, so that we're going to draw the arc instead. So then we're going to do our update and draw from our main game file, mycanvas.js. First, let's just copy this. Oops, Control Z is my friend. Let's copy this set of, I believe it's pretty close to the same as, I'm gonna copy the arguments for the mover class. And it's pretty much the same as the sprite arguments, because we're gonna actually instantiate a mover. And we're gonna instantiate a mover in mycanvas.js, and then we're gonna draw it, and we're gonna update it, increase its speed, and then draw it. Okay, so right here, we're going to create our mover, and we're going to say mover. I believe it's var mover equals new mover. I think that's how you do it in JavaScript, I'm pretty sure. Okay, so we're going to send it null for the sprite sheet. Then we're going to send it the starting x and y value of the sprite. Let's just do it at 200, 200. Then we're going to do the change of x and change of y. That's going to go right into the velocity. So let's have it going down and, no, up and to the right. So we'll do a negative, we'll do a 0.5 pixels to the right, and a negative 0.5 pixels up. That's our x and y. Now we're going to do sprite width. Let's just do, that's going to be probably our radius. So let's just do 10. Sprite height 10, because we're just doing a height, and we're just doing a regular size 10 arc or ellipse. Source location x and y. Am I using the right stuff here? Okay, so sx, sy, swidth, sheight, those we're not going to actually use. So parent width and parent height we will use. So let's go ahead and just put 0 for source location, because we're just drawing an arc. We're not actually using a sprite sheet. We're sending null for the sprite sheet. Okay, so we got 200, 200, 0.5, negative 0.5 for movement, 10, 10 for size of the arc, or for the circle size, and source location x and y 0, 0, since we're not using that. Width and height, let's go ahead and do 10, 10 there for source width and source height, but I'm pretty sure that we can do 0, 0 because we're not using it in this example. And canvas width would be the W that we have up here and the H that we have up here for window height. Okay, so we have our mover instantiated now. Hopefully there's no mistakes there. And we have it going with a velocity of 0.5 and negative 0.5. So if we look at our mover, we'll see here that dx and dy are assigned to the velocity. Our location is assigned to x and y. And our acceleration is given to 0. Now our mass, it looks like we're not passing that in. So that's just going to be nothing for now. Oh no, looks like mass. We've got to send our mass the first thing. Okay, so I copied the wrong, this is wrong. Okay, so let's not do this. Looks like I didn't put mass in there. Okay, let's get rid of that. Let's do this. Let's just copy this one and make sure it matches. Okay, so let's go back here to where we instantiate our mover. Get rid of this guy because that's obviously wrong. Because we didn't do mass. Okay, so let's do, okay, so image null, mass. Let's do, it's not going to really matter because we're not using it yet. Let's just do 10. The x value for the mover is going to be 200 and 200. Now we're doing dx, dy, width, height, sx, sy, swidth, sheight, parent width, parent height. Okay, I think we're good. So now for the update, we just got to go here to mvr.update. And then for the draw, we just got mvr.draw. Okay, and our game loop calls update and draw down here. So we have an instantiated mover, and we're going to make it move around. And if you look at the mover's update, if we go to the mover's update is going to be, looks like we got to send it to key state and FPS, but let's just omit them because we don't really do anything with it here. So I'm just going to take those out. Okay. So the update changes the velocity, location, acceleration. We check the edges to see if we need to bounce back. We constrain the speed of our vector. Okay. And then the draw, we're sending in a null image, so it's not going to draw our sprite sheet because you can actually use this to build like an enemy sprite, like a zombie going back and forth or something like that. And you wouldn't have to use your sprite class. You could use a mover class that's fairly similar. But since we're sending it no image, we're going to actually just be drawing this arc based on the radius. Now, how do we set the radius? If we go up to the radius up here, how are we setting radius? Radius, oh, it looks like we're taking the width divided by 2. Where are we passing in the width? And why is this called x mover? That should be just x. Okay, and it looks like somehow that got into there too. Okay. All right. Radius is going to be the width that we pass in divided by 2. What do we pass in for the width? Do we pass in 10? Width. We pass in, yeah, we pass in 10. So let's actually make that, let's make it 50. So it'd be 25. You don't need to change both of them because we're only using one of them, but that's fine. Okay, let's see if we actually get something drawing to the screen. Okay, cool. Let's see if it bounces edges. Okay, so it's going in the direction that I wanted it to go. It looks like that upper level clear screen is not working well. Okay. So let's go ahead and fix that little clear rect. It looks like I'm starting the clear screen at 30 pixels down. So let's go 0, 0 with that. And let's make this mover go a little bit faster. Let's go ahead and do negative 1.5 and positive 1.5. Okay, so we'll get our mover moving in more of okay, cool. All right, so we're making everything work for us. Okay, now let's say that we wanted this to move down and to the left. So, and let's say we want it to be a steep slope. So what we would want to do is if we want to move it down and to the left, and we want the slope to be steep, that means that we want to travel quite a ways with the y value, and we want it going down, so the y value, which is going to be the change of y, which is going to be the velocity of this guy, we're gonna want to set the velocity to if we want it going down and to the left. We're going to set the velocity to down is a positive y. So let's do a positive. Let's do 3. And then if we're going to the left, we're going to do a negative 1. Down and to the left. Okay, so what I want you to do here is I want you to play with this and start kind of understanding how this vector works with direction. And these two numbers you can change around and just see what happens. Remember, this is the change of x and the change of y. So every time this frame is run, we're going to apply, or we're going to add this vector to the velocity vector. So let's look at that. Our dx and dy is coming in as a negative 3, or what is it? Negative 1, 3. A negative 1, 3. So velocity is going to be negative 1, 3. So every time through the loop, we know that velocity, the velocity vector is negative 1, 3. Okay, so every time, and let's say that our location, and I'm going to zoom in on this, and let's take some of this other stuff out. I want to show you kind of how adding vectors works. And that's what this add function is doing. I'm going to show you what this add function is actually doing. Okay, so our change of x and change of y is negative 1, 3. Our acceleration, our location is starts out at 200, 200. Okay, so let's say we take velocity, which is going to start out as negative 1, or it's going to be negative 1, 3. And we add it to acceleration, which acceleration is going to be 0. So that's fine. Acceleration, let's just take and not even think about. Let's talk about this one right here, this location. What's actually happening when we change the location. So ignore the velocity with acceleration for now, because it's just an extension of the understanding that we're going to be talking about with the location. So let's say our location is at 200, 200. And I say, okay, take our current location and add the velocity. So if I'm going to add the velocity that contains negative 1 and 3, so then that means that I'm going to take the x value of 200 and add a negative 1. And the result is going to be 199. And the mover is going to move to the left. And then I take the y value, which is going to start out at 200, and I tell it to add the velocity y, which is 3. Which means now that the y value is now going to be 203. So it's going to move down faster than it moves to the left. But every time this frame runs, this velocity, your location, is going to complete these instructions by adding the velocity to the location vectors. And that's literally taking the velocity x, which is negative 1, and adding it to the location x. The velocity y, which is 3, and adding it to the location y. And then we have our new location, 199 and 203. And then the next one will be 198. The next frame will be 198 and 206. And so forth. And so until you add some deacceleration or acceleration to the velocity, your location is always going to be changed based on the velocity, and you can change your velocity based on the acceleration. So you can think about the acceleration as being the change of the change. So you're driving down your car, and you're changing your location based on your velocity, and you're going a constant 35 miles an hour. And then within a certain slice of time, you ram the gas pedal and you release the gas pedal. Well, you've just added to your velocity at that particular slice of time, which will then increase your location because your speed's increased. So think about velocity as being the steady change of location, and the acceleration being the change of that change. It literally is, you're changing your location going down the road at 35 miles an hour. If you want to change how fast you're going, you step on the pedal, and that's your acceleration. So acceleration changes velocity, velocity changes location, and the acceleration works just the same as adding the velocity to the location. It's just literally an x plus x, y plus y scenario. So you take the velocity's x and add it to the location's x, and the new location's x is the sum. You take the velocity of y and add it to the location y, and the new location y is its sum. Going back to that PowerPoint of vector addition, that's pretty much what you're mostly going to be doing. And you can also kind of think about it, because when we're going to be applying forces, we can add a force to it. We can do vector addition to add forces to, like a wind force or whatnot, to this. Okay, so here's your goal. I want you to add 3 more movers. And here's an extra credit for you. If you can add the mover as a list or create a list or an array of 4 movers and have them moving around the screen, you get an extra, you get double your points. So to finish the assignment for this week is add another 3 movers to this particular, to this right here. And I'll give you a hint on how to do that. You can do it all from within game. Your canvas right here, you just have literally more of these, and then you call the draw, and then you call the update for each one. You call the update and the draw. So you can add, you can just literally take this, copy and paste it, and hard code it in. But if you want the extra credit, you have to do it as a list or an array. And I'll add that to the assignment. Okay, so here's the 3 things that you really need to know for this module. What vector magnitude is, what normalization is. A basic understanding of velocity, location, and acceleration, and how they're applied. And then, of course, vector addition. Those are the main points for this whole module. Okay, so have fun with this. Start playing around with this velocity, these velocity values. Play around. If you do add more movers, maybe try to do a random generation of velocity. Try to randomly generate those numbers when your program starts. So, thank you. We'll continue with adding force using the addition, vector addition, for next module.